Our final video for this week is going to be about binary search trees. Now, remember last time we talked about 3 different methods for traversing a binary tree: pre-order, post-order, and in-order. The pre-order was where we visited the root first, and post-order the root last, and in-order the root in the middle. We're going to define a binary search tree as a binary tree whose vertices have values assigned so that any value assigned in the left subtree is always less than the root, and any value assigned in the right subtree is always greater than the root. Keeping in mind that these trees are recursive, so this has to hold for all subtrees of the tree. This is one of the trees that we used in the previous video. So now we want to know, is this a binary search tree? 60 is the root, and at a glance I think we can see that all the values in the left subtree are less than 60. And all the values in the right subtree are greater than 60. But that's not sufficient to say it's a binary search tree, because we have to see if this is true for all the subtrees. So if we look at the left subtree of 60 and the root of 41, all of the vertices in the left subtree of 41 are less than 41, and all the values in the right subtree of 41 are greater than 41. Again, if we look where the root is 53, all the values to the left of 53 are less than 53, and to the right of 53 greater than 53. So if we look at any given vertex and look at the subtree where that vertex is the root, does the property hold? And if it does, then the tree is labeled in such a way that it is a binary search tree. So I think we will agree that this one is labeled in such a way that it is an example of a binary search tree. We also used this tree last time, and it's a smaller tree, so I think it's more quickly examined to see that it too is a binary search tree. Recall that when we did an in-order traversal, meaning we visit the root in between the left and the right, that we produced the following sequence below. 1, because we visited that one first, then it's root 3, then it's right subtree 6, where 6 is the root, which makes us go 4, 6, and 7. So in other words, when we used an in-order traversal of a binary search tree, then what we get is an in-order result. That is, the numbers below, notice, are in increasing order. So that's the whole, what's going on here behind the scenes is that we are assigning values to these vertices. We're placing the known values so that when we do an in-order traversal, that's exactly what we get. We get the values in order. Now, this represents a data set, and data sets are always changing. So a question would be, if we have a new piece of data, we want to add it to our tree, how can we add it so that we maintain the order? That is, it's still a binary search tree. So for example, 5. 5 is not there yet. Suppose we wanted to add 5. Since 5 is less than 8, we go to the left, but 5 is greater than 3, so we go to the right. 5 is less than 6, so we go to the left, but 5 is greater than 4, so we go to the right. So now, to add 5, 4 would have a right child, and they would be labeled 5. And if we did it that way, when we traverse in order, we would have 4, 5, and 6 as the order in which we would produce, or the order in which we would do the traversal. Let's do another. Let's suppose this time we want to add 9. 9 is greater than 8, so we'll go to the right, but less than 10, so we'll go to the left. 10 does not have a left child, so that's where we would place the 9. The new vertex label 9 would be the left child of 10. This time we didn't have to go so far. This time we only went to level 2, where before when we added the vertex for 5, we had to go all the way down to level 3. Let's see, 1, 2, level 3, because we started at level 0. Not only did we have to go to level 3, we had to increase the level and make 4 have a right child. So what we would really like to do is to have a binary search tree where the height, or the number of levels, is as few as possible. So let's look at one more example. What if we want to add 50 to this one? 50 is less than 60, so we go left. Greater than 41, so we go right. Less than 53, so we go left. But greater than 46, so we go right. So our new vertex would be the right child of 46. And again, in this example, we did not have to increase the number of levels. But if we look at, I'll go back up to 60 and look at the right child, 74. We noted earlier that 74 did not have a right child. So there's an entire subtree missing if we were to think of this as a complete tree. We could actually move some vertices up so that we could have a binary tree without it having so many levels. And why we would want to do this is if we're ever traversing the tree looking for a particular vertex, the fewer levels, then on average, the fewer number of vertices we would have to visit. So let's see if we can redo this tree where we don't have so many levels. So here is a redrawing of the tree. It has the same vertices as labeled before, but now where we had 4 levels, this one only has 3. We haven't disposed of any vertices. We've only rearranged the vertices so that we have as few levels as possible. Is it still a binary search tree? Meaning, do we still have the property that everything to the left is less than the root and everything to the right is greater than the root? We can make some spot checks. Everything to the left of 60 appears to be less than 60, and everything in the right subtree is greater than 60. If we look at, say, to the right subtree at 65, everything to the left of 65 is less than 65, and to the right is greater than 65. So it is a binary search tree, which means if we do an in-order traversal, we will visit each of these in order. And if we are looking for any particular vertex, we will not have to go more than 3 levels. This motivates the next definition. So a binary tree is balanced if for every vertex, the number of vertices in its left and right subtrees differ by at most 1. In other words, for this property to hold, the tree needs to be as complete as possible. And if a binary search tree is balanced, then it has the shortest height possible. And the shortest height possible allows us to perform a search on the tree with as few, on average, visits as possible. So I hope you've enjoyed your excursion into what is commonly called theoretical computer science. Binary search trees are a mainstay tool for computer scientists when designing a data structure, so that when you search the structure, you can be as efficient as possible by making the fewest number of traversals.